Hello, Cape Town. I'm sorry I can't be there in person. This is going to be the fastest review on ULXs that you've ever seen in your entire life. I won't be talking about everything, obviously, but there'll be a review landing hopefully this week by myself, Jean-Pierre Lesaute, and Andrew King. So hopefully that will cover some of the stuff which I don't have time to discuss. So for those of you who are as yet unaware what ULXs are, I think I have to mention that before talking about the pulsars. They're empirically defined objects, so they have to have luminosities above 10 to the 39 ergs per second. You in the crowd are already aware well, that's almost certainly going to be an issue when we talk about physics. Many of the ULXs that we observe are persistent, so every time we go back to them, they're on. Some of them appear transient. In fact, some of the most interesting ones are transient. And we now know of around about 2,000 of these objects out to around 500 megaparsecs. The obligatory picture of the Cartwheel Galaxy just shows some of those ULXs in a star-forming ring, which also gives you fairly important clues as to their nature. Now, again, that luminosity is somewhat of a problem, especially now we know that ULXs almost certainly, or the vast majority of them, are super Eddington accretors. Now, it was already known for quite some time that neutron stars could go above 10 to the 39 ergs per second. This wasn't a particularly huge revelation in the last 10 years, but what was a major discovery was in 2014, a ULX was found with pulsations, and it was well above 100 times Eddington for a neutron star. So this is a famous result by Matteo Becchetti and the New Star team from 2014, where pulsations were discovered with around about a period of 1 day. One second, and it's incredibly bright. So it's telling us immediately that neutron stars are going to be a common component of the ULX population. And this is a really exciting object in M82, and you can see on the plot on the right, you can see the pulse fraction, but also the pulse frequency. So initially it looked like it was spinning up quite rapidly. Over longer time scales, it looks like it's actually spinning down. It also shows some really interesting behavior in terms of glitches. So there's a really wide phenomenology here to be explored and better understood. Now, this is a very hard slide to take in, especially at the time of day that it is there. As I say, the review is coming out where you can look at this table as much as you want. This is basically an amalgamation of all the ULX pulsars that we know of. You can see that the pulse period ranges from about 0.4 seconds all the way up to a couple of hundred seconds. The spin-up rate can be incredibly extreme. So in one case, NGC 300, it was 10 to the minus 7 seconds per second. So that's really going some. And we're also able to extract from delta P dot, in some cases, information about the orbital period. So these are our systems. There are approximately 10. This is tens out of hundreds to thousands. Most of the reason we haven't found a lot of the ULX pulsars is down to data quality, but there may be some other reasons as well. But this is basically what our picture is observationally in a nutshell. So some of the key questions which are facing our field at the minute are: how do these systems practically exceed their Eddington limit? How many neutron stars are out there? And how do they feed back into their environment? Now, for the sake of brevity and time, I'm not going to talk at all about number 3. Again, speak to me, email me, or have a read of the review. So what really matters when it comes to understanding these systems is whether or not within our accretion flow, the Eddington limit is reached locally. So what I mean is, in this picture, you can see that I've described the disk as a thin disk. Obviously, theorists, please ignore that because we know that it should flare out. And at some point in the disk, the flux becomes locally Eddington. The radiation pressure is now enormous, so the disk puffs up. And to stay locally Eddington limited down to some radius, it has to lose mass in an outflowing wind. And that wind carries some proportion of the accretion power as kinetic luminosity. Then what we see depends upon where we're looking at the system. If we're edge on, we're probably going to see something relatively cool. If we're going to more face-on inclinations, we start to see harder and harder emission. So the point where this thing starts to really change is around the spherization radius, which is also around the photon trapping radius. That's indicated by this little r SPH. So then the other important radius that we know about in these systems is going to be the Alfvén radius, or the magnetospheric radius. For now, I'm going to ignore the surface of the neutron star. If we have a high-strength dipole field, it's reasonable to assume that the magnetospheric radius will be large, and it could even be larger than the spherization radius, which means that material goes down, it doesn't become locally Eddington limited, and then it starts to free fall onto the neutron star through an optically thick magnetospheric curtain. And eventually it makes its way through this down onto the neutron star itself. An alternative viewpoint is that we have a weaker or more moderate dipole field, in which case the Eddington limit is reached within the thin disk. So you get the spherization radius, you get your outflows, and then the magnetospheric radius is instead reached when the disk is still relatively thick. And then as before, material falls onto the neutron star. One of the key differences here between this picture and this picture then are these outflows, and those outflows can act to collimate the emission within. So we get some amount of geometrical beaming. Of course, eventually that material must make its way onto the neutron star, and then we can exceed the Eddington limit through a couple of different ways. We have the Baskos-Sunyaev model, which allows us to have super Eddington fluxes to the side through a fan beam, but also we can suppress the electron scattering cross-section at energies below the cyclotron energy, so you can actually dump more material onto the neutron star itself. Of course, that is a pretty strong limit, and if more material is falling onto the neutron star than is permitted, then presumably that mass must be lost, but that is still a bit of an open question. And I just wanted to flag some of the recent work done by Zhang and Blaise, where they're starting to explore the nature of these accretion columns at super Eddington rates using split monopole geometries, really searching for photon bubble instabilities. But there's some really fascinating work going on there, which I encourage you to explore. Observationally, we have got some interesting constraints on what that region must look like. If we look at the pulse profile for I'm not going to say a standard pulsar because it's not my field and I might get it wrong, but you can see there's an X-ray pulsar on the right, and you can see that you've got quite sharp pulsations. On the left-hand side are the accumulated pulse profiles of all the ULX pulsars, thanks to many people who provided that information for me. And you can see that for the most part, they're much broader, they're much more sinusoidal. And that's probably telling us that the emission is coming from a larger surface. And there's going to be some really interesting work, especially in a talk by Bykov coming up about reflection and the geometry of these flows. So there's some really important constraints we can probably apply there, although they haven't really been explored in much detail yet. So one of the key things is, what is the magnetic field? What is the dipole field in these neutron star systems? There are different ways we can go about doing it, and this is by means not exhaustive. One way is that we assume the luminosity is a consequence of Baskos-Sunyaev model and suppressed cross-section. So this is work that Alexander has published, and you can get really quite extreme dipole fields. So we're talking about quite strong magnetars here, above 10 to the 14 Gauss. You can assume that the system is near spin equilibrium. That gives you a lower range of dipole fields. You can assume the system is not near spin equilibrium and just use Gaussian Lamb models. That tells you these things around 10 to the 12. Or you can use supercritical accretion models, a lot of the work done by Andrew King and Jean-Pierre Lesota, and those tend to give a range of fields between 10 to 11 and 10 to the 13 Gauss. So there's some level of consistency there around systems which are not, around field strengths which are not daft for the high mass X-ray binaries we know about, but there's also a more extreme model for creating very strong field magnetars. And there are other ways as well that I haven't talked about, involving looking at precession, looking at the limiting luminosity for going into propeller states. So, but there's a lot out there. And a lot of that is a bit unambiguous because we're looking at the accretion flow. We don't really necessarily know which regime we're in. There's a lot going on. So what we really want to do is find an unambiguous indicator of what the field strength might be. And I believe that the very first one and the strongest one is the detection of a CRSF in a ULX in M51. This is work led by Murray Brightman back in 2018. And you can see the feature around 4.5 kilo electron volts, but it's relatively narrow for an electron CRSF. Of course, I've given the equations there. This is not an audience where I really need to provide them, but I felt obliged to. If it was an electron line, the field would be less than 10 to the 11 Gauss. If it's a proton line, and it is quite narrow, so perhaps it is a proton line, that implies more like 10 to the 15 Gauss. So this would favor the magnetar model. But if it is this picture, then what it means is that it's defined what the geometry of the accretion flow should look like, and also therefore what the X-ray spectrum should look like. So we should have a thin disk down to the magnetospheric radius, and that is subcritical, so it should be less than Eddington. So it's given by the sort of the pinky purple line. Then we should have the optically thick emission coming from the curtain, which is reprocessing the emission from within, from the fan beam, and also some emission coming out from directly from that column, possibly collimated by from within that opening angle of the curtain. So that's quite an easy thing to go and look at. It's quite a clear prediction. The alternative is that what if this isn't the dipole field we're looking at all? What if we've got this picture? Well, then we should have at soft energies a sort of quasi-thermal black body that is above Eddington. We should then still have emission from the curtain, and we should still have our pulsations. But of course, this is now a function of inclination because we've driven these enormous optically thick winds from the accretion flow. So how do we go and test that? Because when you look at that spectrum and you go, well, that's just a curvy line. What do we do about it? One of the things that is quite powerful is using variability. So this is something I tend to use quite a lot. And what those green points are on the spectrum is the covariance. And I do not have time to go into that. It's a really important tool. It allows you to break apart an X-ray spectrum so you can remove some degeneracy. And if you describe that as a soft and a hard component, so you've got those green points, that's one component in the spectrum, there must be something else to provide the soft emission. That soft component is way above Eddington. And you've still got this hard component. So you can then just apply some basic, simple modeling to it, and it predicts the dipole field is less than 10 to the 12 Gauss. So that's at odds with our predictions, but only if the protons are being accelerated by the dipole field rather than a much higher strength multipolar component. And there's a really nice result that's come out just last year about a transient ULX. It didn't go to 10 to the
3 minutes more.
Geez, really? Okay. Good luck. And the dipole field is estimated to be 10 to the 12 Gauss. The electron line that's present indicates it's more like an order of magnitude brighter. And I think that's really telling us that we are indeed seeing a more multipole field with a weaker dipole field. And if that's true, then we've probably got a condition where the magnetospheric radius is within the spherization radius, and we've got some level of collimation by these winds. So I just want to make sure I get through as much of this as possible. In that case, then it means that if we've got these powerful winds and a lot of ULXs, then many of them are going to be hidden from us, obviously, because at large inclinations, we have to look through a large amount of material, for instance, like SS433. Even if we're face-on, then we're going to have a problem finding these neutron star systems because the pulsations will be diluted due to scattering in that funnel. So finding neutron star ULXs is really difficult. Maybe what we should be doing is looking for propeller states, so where we switch off that inner region. In some cases, they will be sub-Eddington because we've killed everything within the magnetospheric radius and the dipole field is strong. But in some cases, the luminosity that's coming out will still be super-Eddington because the magnetospheric radius is within the spherization radius. And I made some recent predictions with some colleagues, and it tells it for quite a large range in parameter space in terms of surface dipole field and accretion rate, the change due to propeller might be less than an order of magnitude, which might make them fairly difficult to find. Fortunately, there are some key predictions in terms of the spectra. So if we're turning off the inner regions in that picture on the bottom right, then what we do with our X-ray spectrum is we get rid of that stuff. The soft emission remains, the hard emission goes away. And there are a handful of ULXs that my postdoc, Andre Gupid-Lacharas, found where this happens, where we have the soft component stationary, basically not doing very much, but in a later observation, the hard component has gone away. If we interpret that as a propeller state, that implies that the field in one of these systems at least is fairly weak, but not inconsistent with other estimates for the ULXs. So this is really interesting new stuff, and it's going to make finding ULXs probably pretty hard. Okay, so the take-home points is that I really haven't described pulsing ULXs at all. There's just really no time to do that. But neutron star ULX is going to be a really important, perhaps majority of the population of ULXs. A lot of the focus now is on working out the field strength, working out the configuration, higher order multipole versus dipole. It looks to me, and from other pieces of evidence, that there are these combinations, and we've barely scratched the surface. The things I would love to talk to people about some other time maybe is field suppression, which is going to be really important in these systems. The ubiquity of winds and what that means for the surroundings, because they're going to push kinetic energy and energy density into the local environment, and what happens on long timescales, because there's some really exciting stuff going on there. And I will stop there. I hope that you at least took in some of that, but feel free to email me if none of it made sense and you want to know more. Thank you very much for your time.